The name Oldsmobile means something special to new car buyers. These people expect comfort, prestige, and smooth operating performance. And the Hydromatic 4T60 automatic transaxle, previously known as the 440 T4, is part of the strong reputation for performance and dependability offered by the larger Oldsmobile front-wheel drive vehicles. For 1991, the new Hydromatic 4T60E makes the 4T60 even better by adding electronically controlled shifting, which provides greater smoothness and reliability. The 4T60E is featured on the 1991 Oldsmobile Toronado and Trofeo, the 98, the Touring Sedan, and the Cutlass Supreme when equipped with the 3.4-liter dual overhead cam V6. This CPT presentation and accompanying course book will concentrate on examining the 4T60E's electronic controls and their diagnosis for transmission and drivability technicians. It is specifically designed to help you make sure a problem is not electrical or related to engine performance before removing the transaxle from the vehicle. For a complete understanding of the 4T60E, including internal mechanical components, you should enroll at a General Motors training center for thorough hands-on training. This high-priority course lasts 2 days and is number 17002.03. Before looking in depth at the new 4T60E, realize that there are 2 versions of the 4T60E, one for 3800 equipped Toronados and 98s, and another for Cutlass Supreme when equipped with the new 3.4-liter V6. While most of the operational and service concerns are the same, the basic differences are the inputs used to make shift decisions and the design for enhancing TCC engagement quality. Now, let's look at the new 4T60E. As a service technician, there is one important point to keep in mind as you begin to understand the new 4T60E electronic transaxle. And that point is to remember and use all the knowledge you have of the familiar 4T60. In fact, let's begin by reviewing some of the similarities the 4T60 shares with the new 4T60E. Line pressure is still channeled through the valve body to apply the clutches and bands in order for shifts to occur. Line pressure is still controlled by the vacuum modulator, and therefore the vacuum modulator affects shift quality. Mechanically, a drive link assembly still carries power to the output shaft. On the output shaft, the various ranges are still supplied through planetary gear sets, where their elements are held or released. Also, a torque converter clutch, or TCC, is still solenoid controlled and provides increased fuel economy. Let's now note the major differences on both versions of the 4T60E. First of all, there is no governor. Vehicle speed data for shifting comes from the vehicle speed sensor, or VSS. The VSS features a stationary magnetic pickup and a rotating toothed ring mounted to the final drive assembly. This arrangement generates an AC voltage signal, similar to the speed sensors for anti-lock brake systems. The throttle valve and cable have also been eliminated, along with the need for setting the cable. Throttle data for shifting comes from the throttle position sensor, or TPS. As you have probably figured out, the 4T60E can eliminate the governor and throttle valve by using data that is already available as part of today's modern engine management system. This data is used to control the solenoids in the valve body. Using this solenoid design allows the number of valves to be reduced from 28 to 14. By being turned off or on, the shift solenoids, solenoid A and solenoid B, work in tandem to produce the 4 forward speeds. Shifting decisions at the solenoids are made by the Powertrain Control Module, or PCM. Since management now includes the transaxle, the name was changed on 3800 engines. On the 3.4-liter V6, it is still known as the Electronic Control Module, or ECM. Regardless, inside the module, there are quad driver modules, or QDMs. For the transaxle, the QDM is the individual logic controller, commanded by the control module to execute transaxle shifting functions. The coolant temperature sensor, shown here below the throttle body on the 3800 engine, also relates to the system. Operating temperature is used to adjust shift points and when the TCC can be engaged. The brake switch disengages the TCC solenoid and therefore is part of the logic and sensor network for 4T60E control as well. The cruise control system is also part of 4T60E control. When cruise control is engaged, the control module modifies downshifts and upshifts to provide more constant vehicle speeds. Engine speed is read by looking at the pulse reference on the electronic spark timing, or EST system, to determine shift points. Let's now note some of the component differences between the two 4T60E variations, beginning with the one for 3800 equipped Toronados and 98s. A unique input for the electronic controls on 3800 equipped vehicles is the Prindle switch found on the case. The Prindle switch tells the PCM which gear range has been selected by the driver. As we mentioned earlier, the familiar TCC solenoid still exists. However, on vehicles with the 3800 engine, there is a new pulse width modulated, or PWM solenoid, which uses a duty cycle to bleed off TCC regulator valve pressure to make the engagement process much smoother. On 98 models, power for the transaxle shift solenoids comes from the 15-amp fuse number 5 in the interior relay center. On Toronado, it's fuse number 6 in the fuse block. The solenoids are grounded through the PCM. The PCM ground is G100 attached below the coil ignition module. On Toronado, the ground is G104. The control logic for the 3.4-liter dual overhead cam Cutlass 4T60E uses several other inputs. On the 3.4-liter, the ECM also looks at the manifold absolute pressure, or MAP sensor, to modify shift points. This is done based on altitude as well as air pressure. The major difference, however, is the use of two normally open discrete pressure switches. The low gear pressure switch detects manual valve line pressure in low gear to notify the ECM that manual low has been selected by the driver. The fourth gear pressure switch reads line pressure in fourth gear to input to the ECM. The ECM uses this information to disable the TCC during 4-3 downshifts. Also related to ECM logic control is the absence of a PWM solenoid on the 3.4-liter configuration. These Cutlass models use a TCC accumulator design similar to the one found on the previous 4T60. Power for 4T60E shift solenoid operation on the 3.4-liter engine comes from the 10-amp ignition fuse in the right side electrical center. As on 3800 equipped models, the system's ground goes through the control module. On the 3.4-liter V6, the ground is G101, found at an engine transaxle attaching bolt.
End Part 1. You should now prepare to take the first part of the test for this course. To take the test, you must have a number 2 pencil and the official student attendance and test form in front of you. Make sure the first 7 digits of the course number printed in Block 9 of the student attendance and test form match the first 7 digits of the course number printed on the back of the course book and the videotape label. If you do not have the correct materials, stop the video and get them. Begin by placing the student attendance and test form in front of you so that the clipped corner is in the lower right. In the upper left-hand corner of the form, you will see a series of circles below the letters A through E. At this time, you will be filling in the test answers only. At the end of this video, instructions for completing the remainder of the form will be provided. This is the only answer sheet you will need for this course. In a moment, you will see the first test question and several possible answers. When you have decided on your answer, completely fill in the circle below the letter corresponding to the correct answer. Since this test will be corrected by computer, it is important that you avoid making stray marks on the paper. If you change your mind about an answer, be sure to erase your first choice completely before marking the correct answer. It is also important to avoid getting dirt or grease on the answer sheet or folding it, as this may cause the computer to incorrectly score your test. As you take this test, remember that there is no time limit. You may take as much time as you wish to complete the test. You may also review the course book or rewind the videotape to find the correct answer. Begin Test Part 1 at line 1 of the test form. Test Part 1. Question number 1. The 4T60E can eliminate a throttle valve and cable because it uses data from the A, VSS, B, Prindle switch, C, TPS, or D, brake switch. Question number 2. The low gear and 4th gear pressure switches on the 3.4-liter version 4T60E are A, ECM controlled, B, normally open, C, normally closed, or D, TPS controlled.
Operation of the 4T60E in various gear ranges is electronically controlled. However, many valve body operations remain the same. The pressure regulator valve continues to control pump output pressure. The modulator valve, in response to engine vacuum at the vacuum modulator, adjusts line pressure for shift quality. The manual valve directs line pressure to shift valves and can override the electronic controls in manual third and manual second. Mechanical hydraulic operation also requires shift valve action, as before, to apply and release bands and clutches. But what makes the 4T60E special are the solenoids and control logic, which direct line pressure to the shift valves. The 2 shift solenoids work in tandem to provide the 4 forward gears. Basically, when energized, the solenoids are closed and prevent fluid from passing through them. When the solenoid's ground is removed, it de-energizes and the fluid is allowed to exhaust or pass through the solenoid. Each of the 2 solenoids has 2 states, on and off. That's how 4 gears are available. 2 times 2 equals 4. In first gear, both solenoids are on. In second gear, solenoid A goes off and solenoid B remains on. For third gear, both solenoids are off. In fourth gear, solenoid A goes on while B remains off. On 3800 equipped vehicles, solenoids A and B receive power whenever the ignition is on. Ground is controlled by a quad driver in the PCM. To energize the solenoids, the quad driver provides a ground. To de-energize the solenoids, the quad driver removes the ground. The PCM makes shift point decisions based on input from various sensors. The two most important are the VSS and TPS, which identify vehicle speed and throttle position, respectively. Other inputs come from the brake switch, engine speed, and cruise control system, as well as the coolant temperature sensor. On 3800 equipped vehicles, the Prindle switch is also part of this PCM input network. With the 3.4-liter V6, the sensor network differs slightly. The Prindle is not used. However, manifold absolute pressure, low gear pressure, and fourth gear pressure are used. Regardless of the engine configuration, this sensor network helps ensure the smoothest shifts possible under a variety of operating conditions. Let's review how the electronics control basic hydraulic action in the valve body through the 4 forward gears when the overdrive range is selected. To begin, both solenoids are on and fluid is directed to the forward band to complete the first gear hydraulic circuit. When the PCM determines second gear is needed, solenoid A is turned off and fluid is exhausted through it. Spring pressure moves the 1-2 shift valve and fluid applies the second clutch for second gear operation. For third gear, the PCM turns off solenoid B while A remains off. Exhausting fluid through B causes the 2-3 shift valve as well as the 3-2 and 4-3 downshift valves to shuttle. This directs fluid to the third clutch for third gear operation. When the PCM determines fourth gear is needed, solenoid A is turned on. Fluid is stopped at A, which shuttles the 3-4 shift valve, so the fourth clutch applies. Part and full throttle downshifts are also made by the PCM controlling the solenoids. When the PCM senses light throttle acceleration, a 4-3 downshift can occur. The PCM de-energizes solenoid A. The fluid venting through A causes the 3-4 shift valve to shuttle back for third gear. Under heavy throttle acceleration, the PCM then turns solenoid B on. With fluid pressure held at B, both the 4-3 and 3-2 downshift valves shuttle and the 3-2 downshift occurs. Manual downshifts made by the driver also involve the solenoids, but in a lesser role. In each case, the solenoids energize and de-energize as they would in the automatic shifting mode. However, the manual valve performs the lead function by directing fluid to additional components to provide the engine braking feel associated with manual downshifting. Hydraulic gear selection overrides electronic shift commands except in manual low. Manual low is always electronically controlled whenever the VSS shows speeds of 35 miles per hour or less. As with the previous 4T60, park, reverse, and neutral are always hydraulically selected. In these cases, both solenoids remain on. In addition to shift solenoids A and B, there is the TCC on-off enabled solenoid. And on vehicles with a 3800 engine, there's the PWM TCC solenoid. These two solenoids work together for TCC operation. The TCC enabled solenoid receives power from the relay center and functions as before to engage and disengage the torque converter clutch. When engagement is required, the PCM provides a ground for the TCC enable solenoid. The PWM solenoid also receives a ground from the PCM. However, this ground is pulse width modulated, and the PWM solenoid therefore cycles at a specified frequency. The PWM's function is to make the torque converter clutch engage smoothly. When the TCC solenoid is energized to hold fluid for torque converter clutch apply, the PWM solenoid starts at a 100% duty cycle bleed and reduces bleed so clutch apply is gradual. The rate of bleed at the PWM solenoid during actual engagement can be varied anywhere from 75 to 0%, depending on how much TCC slip the PCM decides is necessary based upon engine operation conditions. When TCC is to be disengaged, the TCC solenoid exhausts fluid, which allows the converter clutch apply valve to move and route fluid to the release circuit. As we've mentioned, TCC operation with a 3.4-liter dual overhead cam engine differs. These models don't have a PWM solenoid and use an accumulator similar to the 4T60. When the ECM determines that the TCC can be engaged, the ECM grounds the TCC solenoid and fluid stops exhausting and moves the converter clutch valve. The fluid also enters the TCC accumulator assembly. As the fluid is absorbed here, an increasing pressure is built up and the torque converter clutch plate applies. Basically, with this design, hydraulic pressure is cushioned by the accumulator at the moment of engagement for smoothness.
End Part 2. You should now prepare to take the next part of the test for this course. If you are unsure of the answer, you may stop the tape to think about the question, review the course book, or rewind the tape and review it before answering. Test Part 2. Begin this portion of the test at line 3. Question number 3. The shift solenoid operation for third gear is A on, B off. B, A on, B on. C, A off, B on. Or D, A off, B off. Question number 4. The shift solenoid status in reverse gear is A on, B off. B, A on, B on. C, A off, B on. Or D, A off, B off. Question number 5. To begin TCC apply in the 4T60E for the 3800 engine, the PWM solenoid starts with a duty cycle bleed rate of A, 100%, B, 80%, C, 60%, or D, 50%.
Although the 4T60E is an electronically controlled transaxle, basic automatic transaxle diagnosis procedures are still important to properly service a customer's vehicle. As before, proper diagnosis must begin with a complete and accurate repair order. It also helps to have a customer concern and/or road test sheet that plainly states the what, when, and how of the problem. At the vehicle, the first step is fluid inspection, which is as important to the service technician as a blood test is to a doctor. Check level as well as condition, particularly noting extreme discoloration or a burned smell. If you suspect a problem with the fluid, refer to the service manual for traditional diagnosis and service. And as with any automatic transaxle or transmission, engine performance is essential to transmission performance. It's particularly important with the 4T60E for several reasons. First of all, there are shared sensors. The TPS, VSS, and coolant temperature sensor, for example, supply data for the 4T60E as well as engine management. Another thing to consider is a vacuum leak. Today's sophisticated ECMs and PCMs can compensate for a vacuum leak and provide seemingly normal engine operation, while the weak vacuum signal at the modulator will cause harsh shifting. Because of the integration of transaxle control with engine control, the electronics of the 4T60E must be diagnosed first before investigating internal mechanical operation. There are two diagnostic sequences based on the service engine soon light. When you find the service engine soon light on, or the customer stated it was on during the problem, the diagnostic procedure is as follows. First, read all transaxle and engine-related codes and repair the cause. Then, after clearing codes, road test the vehicle to determine if the problem is corrected. If the transaxle operates correctly, stop. But if the problem still exists, continue with the functional test. If the service engine soon light is not on, or was not on when the problem was experienced, then begin by reading, recording, and clearing codes. Then perform a road test and read any codes and repair the cause. If a problem still exists, continue with a functional test for an incorrect shifting condition, or vacuum and pressure testing for shift field concerns if necessary. Let's review each of these steps, beginning with reading codes. To read codes, it's best to use a bidirectional scan tool such as the T100 or Tech 1. Although the T100 offers powerful diagnostic and vehicle data information, we're going to use the Tech 1 to make photographing the procedures easier. The Driver Information Center on Toronado models can display shift operation. However, a scan tool is used on these models for transaxle diagnosis. With the Tech 1, you must use the 87-91 Plus cartridge. Install the Tech 1 with the ignition off. Then turn the key on and input the proper vehicle and engine information. When ready, the Tech 1 will let you perform a variety of functions. To read trouble codes, merely press F2 from the main menu. They will output in order from the lowest to the highest. And although manual code reading is possible, a scan tool can make your diagnosis more efficient. At the Tech 1, all codes, current and history, are displayed. Codes related to the 4T60E with a 3800 engine are codes 14 and 15 for the coolant sensor circuit, high or low, code 16, which identifies a system voltage problem, codes 21 and 22 for the TPS circuit, code 24 for a VSS circuit problem. Code 26 identifies a quad driver problem. Code 31 for the Prindle switch circuit. Code 36 indicates a shift problem with solenoid B. And code 38 identifies the TCC brake switch circuit. Note that there is no specific code for shift solenoid A. There are fewer codes related to the 4T60E with the 3.4-liter dual overhead cam engine. Codes 14 and 15 are for the coolant sensor circuit, high or low. Codes 21 and 22 are for the TPS circuit, and code 24 is for a VSS circuit problem. Most codes involve diagnosing the circuit with the Tech 1. In fact, you can watch various circuits operate with the Tech 1 to verify proper status. You can see the voltage at the TPS. You can see vehicle speed at the VSS. You can also energize and de-energize the shift solenoids as well as the TCC-enabled solenoid. All this same ALDL data stream information can also be viewed with the T100. It can also be printed out for further study or customer consultation. Of particular note is the Tech 1's ability to take a snapshot of a circuit during operation. Pressing F3 allows you to select snapshot options. This is especially important because it is possible that a sensor has not failed, but rather the data it is sending is not within the system's required parameters. Here's an example. Let's say the TCC won't engage, and there's no code, or repairing a code will not fix the problem. It is possible that a bad thermostat will not allow the engine to get up to operating temperature for TCC operation to occur. There's obviously a problem with expected operation, but everything is working correctly as far as the ECM can see. You can discover evidence of this on a road test by taking a snapshot of the coolant sensor circuit when TCC operation should occur. The snapshot will verify the engine is not yet up to operating temperature. Another tip when diagnosing codes is the importance of wiggling harnesses and connectors while monitoring circuits. This will help you find possible causes of intermittent conditions. Let's go through a sample code diagnostic sequence on a 98 with a 3800 engine to see how it's done. We'll use a code 36, which identifies a shift solenoid B problem. Please note that a code 36 will not identify all solenoid problems. That's why a functional test, which we'll cover in a few minutes, is so important. Also, before beginning code 36 diagnosis, realize that if you find a code 26, 36, and 38 stored together, there is an open in the shift solenoid power circuit up to the PCM, and doing each code individually won't be necessary. Begin by checking for a blown 15-amp fuse number 5 in the relay center. A code 36 can have several symptoms associated with it. For instance, with the overdrive range selected, the transaxle could be forced into third gear only if solenoid B failed off. Or there may be first and second gear operation only if the solenoid failed on. In either case, manual second and third will be available. For code 36 diagnosis, begin with the ignition on and engine off. Disconnect the harness connector at the transaxle and use a test light to jumper between connector terminals E and F and then E and G. In both cases, the test light should come on. If the light is off for both jumpers, the power circuit up to terminal E in the harness should be checked for an open. If only one of the jumpers didn't work, check for an open in that solenoid circuit to the PCM. Since both circuits worked, we continue by disconnecting the green connector at the PCM and jumper E to F and E to G with the test light again. This time, the light should not come on. If the light came on in either case, check for a short to ground in that solenoid circuit. Since our test light didn't come on, we continue by checking the internal resistance of the shift solenoid circuits. At E and F and E and G, you should find 20 to 40 ohms. If the resistance is correct, either the connector is bad or there's an internal transaxle problem. Look for a possible stuck shift valve. If, however, the resistance is out of spec, repair the transaxle's internal wiring or the suspect solenoid. With the problem corrected, you'll want to clear codes. Merely press F4, then F2 on the Tech 1, or pull the PCM fuse number 5 at the relay center for at least 2 minutes. The Tech 1 is very helpful in diagnosing electronic operation of the 4T60E. The course book for this CPT has thorough coverage on Tech 1, 4T60E capabilities. Regarding the T100, be sure to look for a CD-ROM update later in the model year that will provide complete diagnostic sequences and routines for 4T60E troubleshooting. Another diagnostic tool is J38791, known as the Transmission Test Box. The test box lets you monitor and activate many 4T60E functions. It can be used in the service bay with the vehicle raised and on road tests. There are pinout jacks, switches to activate solenoids, and LED indicators to view the status of circuits. Road testing the 4T60E for the most part is identical to the 4T60. Be sure to try and duplicate the customer's concern. However, before leaving, always remember to apply the brakes and move the selector to reverse, neutral, and drive. Engagement should be quick and positive, but not harsh. To start the road test, place the selector in overdrive and note the upshifts for timing and quality. Check both part throttle and full throttle downshifts. Also check manual downshifts and verify TCC operation by noting an RPM change. On a 4T60E road test, you can use the Tech 1 to see solenoid shifts occur and take snapshots. However, if you initiate shifts with the Tech 1 on the road test, be sure the shift lever remains in overdrive at all times. Otherwise, solenoid shifting could lead to vehicle damage. There are road test restrictions for the test box as well. See the course book for this CPT. Important to diagnosis, the functional test checks the condition of both solenoids and should be done if there are no codes or all codes have been serviced and a problem still exists. Above all, the functional test is always performed before beginning mechanical or internal transaxle diagnosis. The functional test can be found in your service manual, section 6E, and uses a test line and the Tech 1. On a vehicle with a 3800 engine, this procedure is very similar to Code 36 diagnosis we covered earlier. However, we're going to use the Tech 1 and the test box to see how a functional test can be done when the 4T60E is mated with the 3.4-liter V6. Begin by separating the electrical connector at the transaxle and installing the test box between the harness and transaxle. Be sure to use the 3.4 harness on the box. The power ground lead for the test box goes into an extra cigarette lighter type adapter powered by the battery. Next, with the ignition off, connect the Tech 1. Then turn the ignition on. At the Tech 1, input all vehicle information. Enter the field service mode so the ECM will supply ground to the shift solenoids. On 3.4-liter models, ground will also be supplied when the ALDL is grounded or the engine is running. Note that 3800 equipped models are different, as the solenoids receive power and ground whenever the ignition is on. The test box LEDs for solenoids A and B should both be on. If the light doesn't come on in either case, look for and repair an open in the power circuit to the solenoids. If one of the LEDs did not light, check for an open in the ground circuit for that solenoid. If the circuit and connectors at the ECM are okay, then the ECM may be at fault. To continue, exit the field service mode on the Tech 1 and enter miscellaneous tests to check output at each of the solenoids. When you turn solenoid A on at the Tech 1, the LED for A should respond to your commands. Then turn on solenoid B at the Tech 1. Now the LED for B should respond to your commands. If an LED does not respond with your commands, check for an open in the ground circuit for that solenoid. If the circuit is okay, the ECM may be at fault. Since our LEDs flashed correctly, we continue with the ignition off and the engine harness side of the test box disconnected. Now the resistance of the shift solenoids and the internal wiring can be checked with a DVOM. Insert the probes into the ignition pinout and the pinout for solenoid A and then B. You should find 20 to 40 ohms at each shift solenoid to ground. If the resistance is not in spec, there's either an internal wiring or solenoid problem. However, a reading in spec means no trouble found. Continue with Service Manual Section 7, Transaxle Diagnosis. In addition to electrical diagnosis, you must also use traditional diagnosis before assuming there's an internal problem and removing the unit. 4T60E vacuum modulator and line pressure checks are basically the same as on the previous 4T60. Always verify good vacuum modulator operation before testing pressure. To begin, tee in a vacuum gauge at the modulator supply line. With the engine at hot idle and the selector in drive, check the gauge. There should be 13 to 17 inches of vacuum. If you find less, look for and correct the cause. Now, with the brakes applied, wheels blocked, and the transaxle in park, flash the throttle. The vacuum gauge should respond immediately. If it doesn't, check for a restriction in the modulator's vacuum supply line or in the throttle body. Since our vacuum gauge responded correctly, we continue by turning the engine off and connecting a line pressure gauge to the transaxle. Then start the engine. Note the line pressure reading. Again, flash the throttle. Vacuum should go down and line pressure should rise, both immediately. If the pressure gauge responds slowly, remove the modulator and check it with a hand vacuum pump J23738A or its equivalent. Apply between 15 and 20 inches of vacuum to the modulator. At the modulator, note whether the plunger moves inward. Also, vacuum should not bleed down for at least 30 seconds. Also, make sure the modulator valve is not stuck. If line pressure did not respond to flashing the throttle and the modulator system checks OK, the problem could be either a sticking pressure regulator valve or the transaxle oil pump. After verifying modulator operation and throttle response, line pressure should be checked. To begin, connect the hand pump to the modulator. Be sure to plug the modulator vacuum supply line. With a tachometer also connected and the engine running, be sure to set the parking brake and apply the service brakes. Apply 18 inches of vacuum at the modulator. Bring the engine up to 1250 RPM and take the pressure gauge readings in all gear ranges. Compare these minimum line pressure readings with the chart in the service manual. To check full line pressure, dump the vacuum at the hand pump. Maintain engine speed at 1250 RPM and again note line pressure readings and compare them with the service manual. Please note that the entire minimum and full line pressure check sequence must not exceed 2 minutes. Also, be sure to heed the caution and always apply the brakes throughout the test. The key point to remember is to always perform thorough diagnosis before removing the transaxle for repair or replacement.
End Part 3. Before answering the last video test questions, please complete the portion of the student attendance and test form that identifies you and your dealership. If this portion of the answer sheet is not completed correctly, you and your dealership will not receive credit or certification for this course. Begin by placing the student attendance and test form in front of you so that the clipped corner is now in the upper right. Print your last name in block 1, located in the upper left-hand corner. putting only one letter in each box. Print your first and middle initials in block 2. Print the name of your dealership in block 3. Your dealership city in block 4. And state in block 5. Be sure to use the official U.S. Postal Service abbreviation for your dealership state. Print your Social Security number in block 6. Do not fill in the block marked dealer code. Print today's date in block 8. Return to block 1 in the upper left-hand corner of the form. Below each letter of your name is an alphabet. Fill in the circle with a letter that corresponds to the letter of your name at the top of the column. Follow the same procedure for the numbers of your Social Security number in block 6. And today's date in block 8. You should now prepare to take the final part of the video test for this course. Remember that the course book accompanying this videotape contains the final part of the test. Test Part 3. Begin this portion of the test at line 6. Question number 6. If solenoid B fails on, there may be A, first and second gears only, B, second and third gears only, C, third and fourth gears only, or D, first and fourth gears only. Question number 7. A weak vacuum signal at the modulator will cause A, early shifts, B, harsh shifts, C, no shifts, or D, late downshifts. Question number 8. When the vehicle is equipped with a 3800 engine, the trouble code for a shift solenoid B problem is A, 14, B, 26, C, 36, or D, 38. You have now completed the video portion of the test. The course book accompanying this videotape contains the final part of the test. Once you have completed the test, you may wish to make a photocopy of it for your records. After photocopying, place the original student attendance and test form in the pre-addressed envelope. No postage is needed. Remember to complete the questions in the back of the course book before mailing the test form to CPT headquarters. Good luck.
The name Oldsmobile means comfort, prestige, and smooth operation. The Hydromatic 4T60E automatic transaxle's electronic shifting will enhance the strong Oldsmobile reputation for performance and dependability. Use your knowledge of the previous Hydromatic 4T60 and what you now know about the 4T60E. Be sure to thoroughly diagnose engine performance, the transaxle electrical controls, and accessible transaxle functions before removing the unit. This is the best way to keep your customers satisfied.